2005, and he directs the Future Interaction Technology Lab, or FIT Lab, as it's appropriately named. He's currently a Royal Society Legal Home Senior Research Fellow, and he's going to present to us today a presentation called Numbers to Die For. Over to you.
Thank you. Well, thank you very much for coming. This is a lovely lecture theatre. Actually, it's a cinema, and I've had a few technical problems which may intrude later, so I'll warn you now. My laptop has to be in the projection room, and I've got a wireless transmitter. And if the wireless transmitter messes up, I have to get closer to the laptop. So I may start giving the lecture right at the back. So, can I ask you, would you like to put your hands up if you're a programmer? I'm a programmer. Yeah, most of you are programmers. Okay. Put your hand up if you've had problems with gadgets. Like I've just had a problem with a gadget. Yeah? Okay, good. And now put your hand up if you've tried doing anything about it. Good. This is what my talk's about. I want to get you excited with fixing simple programming problems which you can easily fix. And I'm going to illustrate it with this Heckler and Koch in a moment. But first of all, I thought I'd show you where I work. And yeah, it worked. This is Thimbleby. It's about 40 miles away from Swansea University. And Thimbleby is famous because it's where Robert Record was born. Robert Record invented the equals sign. And you might think the university is a mess if that's what the coastline looks like, but yep, that's the university on the coast. And 5 miles from the university is Three Cliffs Bay. I guess this thing's handshaking and trying to reduce errors. So I'm going to get a bit closer because it's really distracting having a button that doesn't work. Let's try it from here. So this is Three Cliffs Bay. Now, numbers to die for. Imagine you're with some mates and you're surfing or swimming in the water. It's a great place. And one of you gets into difficulties. So the volunteer is going to run. There's no mobile phone coverage down there. So one of you is going to run up the hill through the weeds and so on, through all the soft sand to the Coast Guard phone, right? So it's about half a mile from the water. So you're going to be out of breath, running, and you're running towards the Coast Guard phone. And the Coast Guard phone was behind me when I took that photograph, and there is the phone. And you're going to dial Coast Guard? You're going to dial 999. Okay, and as you get closer to it, right, and as I get closer to my laptop, right, damn. So I press buttons twice. Well, you saw what it was, didn't you? And let me get much closer. Yeah, it's gone back. So I'll try standing here, much closer to it. So, numbers to die for. This is what my talk is about in 2 pictures. It is how do things like that get produced, sold, and distributed all around the coast of Britain. So, it's about numbers to die for. And if we look a bit closer at this Heckler and Koch, is it going to do it? Yes. There you go. It's got a safety lock on it. Machine guns can kill lots of people by accident. And people have noticed that. It's quite dramatic when they do that. So machine guns have safety locks on them so that simple slips don't cause major problems. And what I'm going to show you is lots of examples of where simple slips from humans in using computer systems of one sort or another create major problems. And what you need to take away from this talk is that you could put in safety locks into systems and it can have a dramatic effect. There you go. First, I'm going to tell you about the bad apple theory. If you've got a bad apple in a barrel, the barrel of apples goes bad, so you get rid of bad apples. It's a very common idea to handle human error. Good people don't make mistakes, bad people make mistakes, get rid of the bad people. And it's wrong. Here you go. Here's the Panama Incident, which you may have heard of. This is the best picture I could get of it. It's a radiation therapy device, and in 2000 it started playing up, and I think 18 people were killed by it, and the 2 radiologists using it were put in prison for manslaughter. And one of them, Oliver Saldana, she was in prison for second-degree murder. So there's been a major investigation of this. It's made by this company, which say, easy to learn, user-friendly tools. What Olivia Saldana was doing was designing the device for collimating the radiation that goes into the patient. So you draw a pattern of this thing on a computer screen, and obviously the smaller the hole you put in this collimator, the more radiation or the longer you need. It adjusts all the parameters, and the computer program lets you draw the shape of the thing. You know, if the clinician says you need a circle or a square or whatever, you draw it on the screen with a mouse. And Olivia Saldana was drawing this thing anti-clockwise, and the computer got the sums wrong because she should have drawn it clockwise. And the Atomic Energy Agency got drawn in to do an investigation, and they concluded, the experts confirmed, that the cause of the emergency lay with entering data into the computerized treatment planning system. In other words, this is a bad apple. A user made a mistake, get rid of the user, in fact, send them to prison. Just highlight that. The cause was entering data. Why did they come to that conclusion? Whereas if I look at it, the user interface should be symmetric under moving the mouse clockwise, anti-clockwise. It's a bug, right? Well, the manual says to validate, the user must validate results carefully, and in particular, at the bottom of that, a user should verify the results obtained through independent means and evaluate any discrepancies. It's the user's professional responsibility to do this, and because the patient got the wrong amount of radiation, the manual says the user made a professional error, which I think's a bad apple thing. Let's have a look at the causes of errors in hospitals. This is a pie chart. Most people die from procedural errors, a few from prescription errors, documentation errors, training, and so on. Miscalculation, which I'm particularly interested in, is about 10% of all preventable deaths in hospitals. And to put this in perspective, did you know more people die in hospitals every year from preventable errors than are killed by road accidents? It's a major problem, but it is, people die on their own with, say, a morphine overdose, and it's not very dramatic, whereas cars tend to make a mess and it is dramatic. But more people die in hospitals from preventable errors. 10% of those preventable errors come from bad programming, which we're all responsible for. Right, here are some facts about medical systems. 93% of nurses make numerical errors, and those are trained nurses. In paediatrics, life is a lot more complicated. 55% of admissions have an adverse drug event caused by a calculation error. This is dramatic. 15% of dose calculations done by trained doctors they use the wrong formula altogether, not just making a calculation error. And it's compounded by hospitals having lots of different sorts of user interfaces. And all of the papers I've looked at say there was no fault with the device, it worked as it was designed to work, so the error must have been caused by the user. Here's another example. This is a photograph of an NHS defibrillator, as it happens, on a railway station. There's a case a couple of years ago in America where a patient got into problems and the family sued the hospital, and Clay County in Montana, this is an extract from the transcript of the case. Under oath, what you can't... sorry for sounding in pause, but I wanted to read this to you, and I've clipped, the top line's been clipped off. Basically, the vendor under oath said that the physician attending the patient should read the manual of the defibrillator before using it. Now, what do you use a defibrillator for? You're supposed to use it in a hurry when people have a heart attack or they have an arrhythmia or whatever. And under oath, the vendor said they should have read it. And of course he made a mistake because he hadn't read it and because it's an overcomplicated device. So, stop rules. You're interested in AI. Stop rules are, when things start to get complicated, when you're exploring the cause of an accident, you have to stop somewhere. Because you could carry on exploring lots of things, but you stop as soon as you find a good explanation. And there are... I'm wondering whether the screen is clipped off at the bottom from the projector pointing down too much. So if you can say the user has made a mistake, well, you can stop there. Why carry on looking for more complicated reasons for the error? And the gadgets these people are playing with are very complicated. So most people, clinical people in particular, are not going to explore the devices for how the devices induce the error. Right. Here's an example story. I've got this from a paper of an arrest caused by a morphine overdose. The patient dies, and the log showed that the nurse gave the patient 55 milligrams. So the device the nurse was using prints on a bit of paper when you ask it to 55 milligrams. But the nurse was told to enter 5.5, sorry. So clearly the nurse is at fault, and the nurse lost a job. Now, because it's a clinical paper, I can't figure out how the device was actually working. But let me give you a story, which I think is very plausible, and I know some medical devices that behave like this story. So here's the screen on the device, and our task is to enter 5.5. So we enter 5, and you might be interested that I have used a high legibility font, as it's called. The device itself wouldn't have used a high legibility font. And you enter dot because you want to enter 5.5. Again, I've got a nice large decimal point. Most devices don't do that because large decimal points are easier to see. And just to remind you, this is what most displays look like. And there are all these things that are designed to make it hard to read. Okay, so back to the problem. We're entering 5.5. And oops, we've made a slip. We've entered 2 decimal points. So what do? You hit delete. And you get 5 point. You now press 5 and you've got 5.5. Okay, that's what we think would happen. What actually happened would be more like this. You type 5 point, you type the second decimal point, and the device can only display 1 decimal point. You now hit the delete button, you now hit 5. So you think you've typed 5.5, but the device has got 55. There you go. So the nurse has corrected an error, but the device has handled the error correction badly. And the nurse loses their job. And again, these things say there's no fault with the device, and what I'm trying to convince you is it is faulty device design all over the place. I'll give you some more examples in a moment. You may have come across Jim Reason, who's interested in errors and what causes them, and this is called the Swiss cheese model for obvious reasons. A hazard goes through various defences, and if no defence is perfect to stop an error. So if the defence's faults all line up, the trajectory from the hazard to the harm, allows an accident to happen. One of the nice things about this model is it means the last piece of cheese is not the only cause of the accident. The person, the operator at the sharp end of the error, the far right slice of cheese, they have holes in them, just like device design, training, hospitals. Why did the hospital buy the gadget in the first place? There are all these slices of cheese that should have stopped the error. It's not the last person in the chain. It's a very good model. So, how do we teach our students? So it may be that nobody here is really doing some programming, but you may be teaching people who go out and work for these companies and program. Here's one of the top books for programming. It's the 3rd edition, so it's a good one that's selling well. It's well over 1,000 pages. It's beautifully written. It's the Bible of the field, and one reviewer said it's the best textbook ever seen. And it says on like page 3 or something, we don't address error handling. So what are we doing? We're training our undergraduates to go out there to ignore errors. And I've just been showing you what happens when that happens. There you go. I was going to give you some demonstrations of Word and Excel, but I can't be in here and using my laptop, I'm afraid. So I quickly made some snapshots of using Excel. I'll go over these quickly. And I would have typed this in front of you to show you that it was not me just making up screenshots for the fun of it. But this is real screenshots I did by typing stuff while you're having lunch. So I'm going to send the conference some expenses, and I'll show you how to do it. You add up the numbers, yep, and you get the total. And I've chosen these numbers to make it easy to do in your head. Normally, you're using a spreadsheet to add up numbers you can't do in your head. If you could do it in your head, you wouldn't need a spreadsheet. So if you add up the numbers like this, by clicking on each number, you add up them separately, and you get 123. Let's use sum to add them up. Any suggestions? This is really useful for doing your expense claims and things. But the expense claims I'm going to send to ASIB are going to be done like this. Right? So I did this, and I can get that. Right? And I'm going to leave it as a little mystery to you at the moment how I do that. But once you've discovered that programs have got bugs in, you can have fun finding out how you can exploit the bugs. So what have we learnt? We get error. People make errors. We know people make errors all the time, and systems should be designed to accommodate the slips that people are going to make. They're undetected. The applications don't provide the sorts of safety locks a machine gun would have, which is obvious for machine gun, but it clearly isn't obvious for Microsoft and all the other manufacturers. And bad design is causing or inducing errors. And I've said 20 years there because Excel has been around for about 20 years. This is or should be a well-known problem. There ought to be a sort of safety lock on it that says, you know, for some reason, I want an honest spreadsheet. You know, when I send off my expenses to finance, they ought to be able to click it and just get accurate numbers rather than ones that are exploiting bugs. And this looks like it's going to be truncated, but I got interested in how do people handle numbers. And I did a search around the web, and I collected a bunch of algorithms that I found on the web of people doing number entry parsing. Down the left, I have written some numbers, some of them with errors, and near the bottom I've got some text, which is an error. First of all, I wrote my own routine, and this is how it behaves. So, given a number, it gives you its numeric value. Sorry, given a string, which is representing a number, it gives you the numeric value, and given a syntax error, it returns error. It's not hard to do. And here's one algorithm I found. Here's another. Here's another. Here's another. Here's another, and because these are all pulled off the web, most of them are written in JavaScript, and I wondered, JavaScript can do conversions itself. Curiously, JavaScript has got two ways of doing conversions, and they don't work the same way as those columns tell you. Okay. What's interesting is when the user doesn't make a slip, you get the right value, and when the user does make a slip, things go wrong in unpredictable ways. There we go. I'm now going to tell you a story about Denise Melanson, who died from a fluorouracil dose in 2006. Most people who die in hospitals, lawyers get involved and hospitals get twitchy about litigation and so on. Denise Melanson's family asked for an investigation into her death because basically, whatever happened, we don't want it to happen again. So it was a very thorough investigation, and the story I'm going to tell you is based on that investigation. There you go. If you want to look it up, it's called a fluorouracil incident root cause analysis. And, right. I've got the gadget at the front, and I've just decided I'm not going to run around this lecture theatre. I could hold it up and I could show you these things. This is what it looks like. And she would have been an ambulatory patient walking around with a strap to her waist with a bag of about a litre of fluorouracil that goes through the pump and then it goes into a body somehow. And here I've got it in, it's been waved around at the front. That's what it looks like. And second hand, and the bag just held up, is a small bag I brought of the sort of liquid she'd be carrying around in a sort of satchel. Thank you, brilliant. And just for interest, this gadget costs about $1,000 second hand, and they cost a lot of money new. So, what's wrong with it? There you have got a decimal point and an up arrow on the same button. The up arrow button changes mode, the decimal point's obviously a decimal point. And various modes it's got there. International regulations say clinicians should not write micrograms using the Greek mu, because a Greek mu can be misread as an M, and a microgram and a milligram differ by 1,000, so this is a good way of causing errors. There are 3 modes on there, and if you press 1, 2, 3, you choose one of those possibilities. In fact, You can go into 9 modes at the moment, but the display is not big enough to show the other 6. So if you hit 8, goodness knows what mode you're going to land in. You have to know it off by heart. And of course notice that you didn't press some other button instead of the 8. And the help button, if you press it now, will give you help for the first 2 lines because the screen is then full and you can't get help for the other modes. And there you go. That one cost me that much. So Denise Melanson goes into the Alberta Cancer Care Centre to get a refill of the fluorouracil and to get it will all be sort of plumbed into a new gadget, and she'll go away from the Alberta Cancer Care Centre and go back home. And the nurse would say, presumably, no, hi Denise, and the nurse goes off to the pharmacy to get another bag and a piece of paper that looks like that. And this from the root cause analysis is a photograph of the actual piece of paper, and here is a photograph of the bag. There you go. There's the bag, and stuff has been blacked out because this is the actual bag. What does the nurse have to do? She now has to program the device to get the right rate of dosage for the patient in millilitres per hour. And to make it easy for you, I have picked out the numbers she has to use. And they're there. You then have to do a sum, and I'll show you the sum in a moment, and you should get 1.2 mils per hour. But unfortunately, the bag has got 28 mils per 24 hours, and 2 nurses did this calculation. One did it in her head, and the other used a calculator, and both of them forgot to divide by 24. Both of them saw it said 28.8 mils on the bag. That's called a confirmation error. You can see something which is wrong and you think you're right, and so they gave the patient 28 mils per hour. The patient went off and 4 hours later came back to the Alberta Cancer Care Centre and said, why is my bag empty? It usually lasts 4 days. And basically they said, oh dear, there isn't an antidote for a fluorouracil overdose. So here's the sum the nurses did, and here's the sum they should have done. So supposing they did it right and they used a calculator, how would they do it? Well, you have to clear the calculator, you do the sum, and you have to remember to press equals. You then get 1.2. But few calculators have got brackets on, right? And I doubt many calculators in the Cancer Care Centre would have brackets on. So you could do repeated division like that. I'm not sure many nurses would know repeated division is the same as dividing by a product. So you might use the memory in the calculator. So you put 96 or 4 times 24 into the memory, and this is the correct way of using the memory. If you don't do it this way, you'll get some other number put in memory, and then you do the rest of the sum, recalling the 96 to do it. And that is the best way, I think, of doing this sum on an elementary calculator. What's worth noticing is if you make any slip, the calculator will just do something else. Calculators are general purpose. They're designed to do any calculation. Any slip in that, they'll just do a different calculation, and you'll get any old number and think it's the right number. How do calculators help you? Here's a typical calculator, and it detects 2 types of error: division by 0 and square root of a negative number. That's not terribly helpful. And here are 2 calculators, which again are right at the front, and I could wave them around. I can do exactly the same keystrokes on them both. And sort of, you can't see me, but you can do the same things like this, and you can get different numbers. And I have a letter from Casio's lawyers for pointing this out. So you're using the left-hand one in the hospital, you pour coffee over it, you pop off to WH Smith to get the other one, something that looks the same, and it isn't the same. They shouldn't be available in hospitals. Here's another example. There's a calculator. Imagine you're doing this sum. The whole point of using a calculator is to do a sum you can't do in your head. So what fraction of the world are the US population? Those are the numbers, and it's going to be dropped off, isn't it? This is the sum you have to do on the calculator, and you've got to remember to press equals, and you've got to remember to press all clear before you start, and you get that. Does that sound right? No? You can try it. I've got calculators at the front. This is the answer it will give you. What's gone wrong is that the calculators are 8 digits and the world population's got 9 digits, and the calculators overflow without telling you, and they just give you the wrong answer. And there we go. And I've no idea what the title of that slide says. So I have entered 1.2.3 into various devices. Okay, so 1.2.3 is obviously a syntax error. The code that these people put in their devices ignores syntax errors and then comes up with some number. The Abbott pump I showed you earlier has got about 9 or 10 modes, and depending on which mode you're in, you can get different sorts of numbers coming up from entering 1.2.3. The Gravesby 3400 is an infusion pump, and it treats a decimal point as zeroing the decimal part of the number. So if you enter 1.2.3, you get 1.2, and then as you enter 0.3, it clears the 2 and you get 1.3. Most Casio calculators ignore second and subsequent decimal points, so you get 1.23. Mathematica gets you 0.36. The reason it does that is that it multiplies 1.2 by 0.3. Excel will give you 0, which will give you a clue to how I got some of the numbers earlier. And Word will give you 1.5. Word, of course, spots the syntax error and thinks you must have missed out a plus sign. So, question is, the sort of the metaphor for this talk, the metaphor is sort of the safety locks on machine guns. What can you do if you have a safety lock that blocks accidental errors causing major consequences? And I decided to program my iPhone as a proper calculator for avoiding the sorts of slips I saw had happened in the death of Denise Melanson. So I built a calculator. There you go. And several things you can see I've done there. I've got a nice large decimal point. I've got a smaller 20 for this part of the number. And underneath it, the calculator doesn't know, but of course the infusion pump would know. I know how, I'm saying if you've got a standard 50 ml syringe, this dose would last 42 hours. If you've got 130 mils, it'll last 5 days, and so on. And what happens if you, for instance, miss out the dose? Oh, sorry. This calculator will detect 35 different sorts of slips that a user might make. So it is, I think, a lot safer than a conventional calculator. So this is entering a dose, the 5.25 grams of fluorouracil. And if you did that, you would get an error rate that you haven't yet said the dose rate per day. And if you enter a number with, for instance, 2 decimal points, you end up with an error message like that, and it tells you what to do about it. So it is blocking certain sorts of slip. It can't detect all sorts of slips, but it detects some of the slips that it can definitely detect, and that we know that programs like Excel, Mathematica, Word, infusion pumps, medical accelerators and so on do not detect. And of course, being a computer scientist, I got carried away and I made a language to enter any sort of statement, not just a number, and you can compile that to a finite state machine. You can colour the states. The green states are ones where the syntax error, there has been no syntax error, so the number is syntactically correct. The red states are where there has been a syntax error, and the amber states are where you've got a prefix of the correct number. You haven't yet made a mistake. So here's an example of what an improved user interface might like, following the Institute of Self-Medication Practices definition of a valid number, which no medical device follows, by the way. So at the moment, I have entered nothing, and the display shows nothing. This, I think, is probably unique for numerical devices. If you switch on a calculator, it'll show 0 point, or possibly 0.0. If it shows 0 point, you can't tell whether you've entered 0 or 0 point or 0.0. Right? So if you've entered nothing, you want an unambiguous display. Because if you go up to a calculator that shows 0 point, if you enter 5, is it going to show 5 or 0.5? You don't know. So this, if you press 5, it will always show 5 because it doesn't display the 0 point first. And it's in the sort of ambery colour to say you haven't finished yet. And if you start entering a number, there I've typed 1 point. No, that is syntactically incorrect according to the Institute of Self-Medication Practices, but it's a prefix of a correct number. You've got to do more. So, yeah, I've entered a second decimal point and it's gone red. In fact, it will be flashing at this point to draw attention to it. And if you correct the error, it's now gone green. And it's suggesting this is syntactically correct, and it doesn't know this is the right number, it just knows it's a well-formed number, so you could enter it. So I've done a lot of work building systems like that. Is it any good? Is it worth doing it? Because clearly all the manufacturers think it's not worth doing it. So I wanted to do an experiment, and it turns out the error rates for entering incorrect numbers are very low, and surprisingly, for like 30 years of people studying this stuff, nobody has got any data about it. So I decided to do a Monte Carlo simulation, which is the simplest model I've done, and it works like this. So think of a dose, for instance 5.5 that we saw earlier, and imagine that you make an error at some rate, for instance about 1% or whatever, and that means you're going to enter this dose that you should have entered, 5.5, as 5.5 or 58 or 5.5 and so on. Yeah? And then you classify what are called out by 10 errors. For instance, if I'm supposed to enter 5.5 and I enter 5.6 or 5.50, those probably aren't significant errors. But the medical profession are very keen on out by 10 errors. So if I entered 55 instead of 5.5, I'm out by a factor of 10. And that is a sort of error that typically kills people. Here is a graph of the Monte Carlo simulations, and the red line is what the Abbott infusion pump would do with numbers. So I've wasted a happy evening studying how the Abbott pump handles syntax errors. I've programmed it, and I've done a Monte Carlo simulation. And along the bottom, I have got the probability of making a keying error, and on the vertical axis, I've got the probability of getting an out by 10 error. Obviously, so on the far right, you are certain to make an error, and the reason it doesn't go up to probability 1 for the red line is that some of the errors you're making are not going to be out by 10. They might be out by 2 or something. Okay, so about 70% of your errors, if you can't enter the number at all properly, they're going to be out by a factor of 10. And you can see from this graph the simulation's rather good. As you reduce the probability of making slips, the probability of having out by 10 errors drops as well. The green line is a simulation of a device that parses numbers the same way, but it blocks syntax errors. In other words, you're almost halving the out by 10 error rate. And this is a graph drawn with smooth lines. That's the normal and improved. And if these I'm enlarging, if you want to improve the error rate, there are various ways of doing it. Yeah? You could have several nurses to agree that they've both got the same number. So then if you want to have 2 nurses, you've got to pay twice the salary. You could make the rooms warmer. That apparently reduces your error rate. You could reduce the stress on the nurses. That reduces their error rate. All standard ways of improving the error rate cost a lot. And the lower the error rate, the more costly it is to improve it. But these graphs down in low error rates, they're virtually linear. And I think it missed my button press. There you go. Think of some error rate. I'm improving it by that much, which is about the same as halving the human error rate. And this halving is constant over whatever error rate your humans have got. And it's only a matter of updating the firmware in the devices. Most modern devices in the hospital, they've got USB ports up their backsides, and they get updated the whole time because the manufacturers are fixing bugs. They could fix this bug and halve the out by 10 error rate. So there you go. There's a paper which has got some data from America. There's an infusion pump that has been killing people in the States, and here is a paper which was written by Kim Vincente, and he used the Freedom of Information Act to get some data about the baseline rates. And he reckons that pump alone, through out by 10 errors, kills somewhere between 70 and 700 people a year in the States. So you could halve that rate for that pump. And obviously it's one of many pumps used in hospitals, and the pump's also used around the world, and so on. So, let me summarise what I've told you. There's the bad apple theory. Good people don't make mistakes, bad people make mistakes. Bad people are bad apples, get rid of them. And if you get rid of them, the organisation loses any knowledge about the error. There's a nice thing, term called the impossible error. If the organisation has sacked the people who've made the mistake, the organisation does not make the mistake. It's an impossible error. Nobody on a ward kills people, because if they do, they get sacked. Nobody in a woodworking shop chops their hand off on a table saw, because if you chop your hand off on the table saw, you stop being a woodworker. So when you go into a woodworking shop, it's impossible. You can't chop your hand off. So people then underestimate the chances of making errors, because they don't know they can make those errors. So the bad apple problem is it's a simple theory. It explains problems and you get rid of the problems, but you're solving the wrong problem. Swiss cheese, Jim Reason's model of the Swiss cheese makes it clear that the last person to touch the patient or the last person to make the error is not the only cause of the error. There are lots of causes of the error. I told you about stop rules. It's tempting to stop when you've got a simple and sufficient explanation of the error. And typically, that's human error. And I was arguing that design error is a much more complicated problem. And if we, as experts in computer science and AI and so on, started exploring the devices, we would find more ways in which errors are induced. I mentioned priming. Many devices encourage you to make errors. They prime you to do the wrong things, and I gave you some simple examples of that. I talked about the Panama accident, and if those of you who remember the Tharac accident, it's astonishing that stuff like this is still manufactured. And down at the bottom it says out by 10 errors. Right? We can halve the out by 10 error rate by blocking syntax errors, which is something I haven't yet come across a medical device that does. And I'm just going to go to the final slides. There you go. It's called Numbers to Die For, and the thing I want you to remember is how easy it is to put a safety lock onto something to make them safer. The idea that I'm trying to communicate in this talk is it going to show me? There you go. Safety locks work. They're trivial, they're simple, and they make machine guns safer. They make things like Excel safer, except Excel doesn't have any safety locks on it. They're not difficult to program. In fact, we may teach programming, but we also teach compiling, and we teach error handling, but somehow the students don't join the two things up. And something like the Abbott pump shows that they had 5 or 6 students implementing number entry error, and they all wrote different number entry routines, and they all handle errors in different ways. Safety locks are easy to program and they save lives, and the final point is you ought to go and do it and tell your students to go and do it. Okay, that's the end of my talk, so I'll come to the front to have any questions or comments. So, for your question, don't ask me to go to the 3rd slide or something. I
see several hands going up. I don't know which one you want to take. I think that was the first hand that went up.
As I recall, one of the recommendations that came out of the official report on the Tharac 25 disasters was that one should always put hardware locks when there's some sort of chance of, operator causing death. And so I see that you recommend safety locks, but suggest that this can be done with programming. I mean, there's no chance, I think, of putting hardware locks and everything. What do you think about that?
That's a good question. Hardware locks are obviously simple when they can be used, and the Tharac accident happened because a lump of tungsten was moved out of the way, and a lock on that would have been a good solution. But most devices are much more complicated, and I think that's a historical report. Nowadays, something like a fly-by-wire aircraft, mechanical things not going to cut the mustard. It's got to be a piece of software.
There are, I think, 2 problems with building in more safety locks, especially in software. The first one is that people become complacent. You cannot assume the same level of vigilance by the people. If it gets safe enough, the people will disregard safety altogether. The other is, in a complex system, the more you program out little errors, the more you ensure that when you make one, it will be a dilly.
Beer? A huge one. Mm-hmm. Yeah, those are both good comments. Your first question, the technical term is risk homeostasis. People have a natural propensity to make errors, and if you make things safer, they then increase the excitement of their job. A good example of this is if you put safety belts in cars, people drive faster. If you make medical devices safer, it's possible nurses will start taking greater risks. And I've just got a grant to start doing experiments with mannequins in hospital wards. We've got permission to call nurses out to play with mannequins, give them infusions, and we can stress the nurses in various ethical ways. Like we can get their mobile phone to ring while they're giving an injection. And we'll find out whether them knowing that the device is safer than most of the devices has a counterproductive effect. But I'm an engineer. Let's say you see a car with loose wheel nuts. Right? This makes the car unsafe. It seems to me it is possibly even a moral obligation for an engineer to tighten up those loose wheel nuts, even if it allows the driver to go faster because the car stops rattling. Right? So the car rattling because it's got a loose wheel means you drive slower, but it's dangerous. The engineer comes along, tightens the wheels nut up to eliminate an engineering problem. The driver may go faster as a consequence of that. And I don't know, they may go off the cliff and have an accident for all sorts of reasons. But I would sleep better if the wheel nuts were tightened. And that is my best answer to the risk homeostasis thing. This is crappy technology, and it shouldn't be out there. We should fix the problems, and then we should find out the consequences of what happens when nurses and other people, people firing ballistic missiles. We should find out what happens when these things are properly designed, and then start solving the social problems afterwards. But when the engineering is a mess, life is going to be a mess for any reason whatsoever. Okay. So, I don't know.
Yes. I want to preface by saying that I think your message is really good, and then I'm going to refute it a little bit.
Okay.
So one of the things we hear a lot these days is how important safety is.
Yeah.
And a lot of things have been compromised to some degree for safety. And a counter-observation is that you have to be really careful when you're worried about such things to balance it versus other needs that people might have. Convenience certainly isn't as important as safety, but when safety is enforced to the extreme, that you get the extreme of inconvenience, then it's actually not worth it anymore. So one thing that you might consider taking into account when you're working on this research is that balance. So some examples I can give, there's actually a lot of cases. A good example that I could give is, you might have a car now, you have cars now that actually detect how close you are to other cars on the road, and they'll actually put the brakes on for you. Is that a good idea? Because it could be that you need to for some reason you need to be closer to that car, or maybe you have a governor on a car to keep it from going above a certain speed, and maybe you have someone in the back seat who needs to be at the hospital who's dying in the back of your car. So there's things you need to take into account when you do that. Another example that's a little less extreme is there's a lot of cases with an operating system where you have to make a decision between how much control to give the user about how the operating system behaves versus preventing the operating system from crashing or running too many programs. There's a lot of balance there. One of the complaints that's frequently leveled against Microsoft Windows is that, oh, well, it tries to know better than you do. It won't let you do certain things that you can do in other operating systems because the user's, quote, not smart enough, unquote, to handle it. So that comes up in a lot of different places in a lot of different contexts. And I think it's worth bringing up here. If we need to move anywhere in terms of safety and software, I think we need to move towards more safety, which is why I fully agree with what you're saying. But I think it's worth always taking that in the context of what the other needs are and balancing.
Okay, thanks for those examples. I think my best answer is safety is a complicated issue, and there are complicated situations that you talked about. Nevertheless, number entry is a simple case, and we could get that right if we wanted to, and there's a motivation to do it. So you haven't argued against that. What you have argued is that people who put in safety systems, they're actually putting in features to make the device sell better, and they're not really looking at the full safety story.
So if we were to take your number entry system and use it as a default for all devices or all situations, I think that would be a mistake. Your finite state machine won't allow anyone to enter 00 as the first 2 digits.
Well, okay.
Which you may want to do. You might be formatting something such that you want all the numbers to have 3 digits.
You may indeed, but the Institute of Self-Medication Practices has studied medical errors, and they have defined the language for numbers. That state machine I put up happened to implement that language. Now, for other applications, Excel, for instance, well, who knows what sort of numbers you want to enter into Excel, and you would have, do you remember the slide before that state machine was the grammar for that language? The system I built, you can enter any old grammar if you like, and you'll get a different machine at the end of it.
I just wanted to point out there's a danger in assuming that once you have one good algorithm, it's good for everything.
No, I was claiming that was an algorithm that was good for Institute of Self-Medication Practices numbers. And no device implements it, despite it being in the rules for about 10 years. So there's a complete disconnect between what the regulators are saying and what the manufacturers are doing. And the hospital procurers are completely unable to check that these devices are failing the regulations that are there already. But you're right, the world is complicated, and you have got to consider all sorts of factors in the real world. But I don't think that detracts from the basic area that in all computer systems I've seen in the real world, us engineers have made a mess of them because we don't care about errors.
There's lots of people wanting to ask questions. Can we take the neighbour of the previous question?
Hi, so coming from an AI perspective, and given that no interface is ever going to be easily perfect, easily designed to be perfect, is there a place for some intelligent systems to be monitoring usage patterns at a general level for all of these devices, because they are used over a number of weeks, months, years, and then highlighting when, for example, someone puts in a number that has never been put in that big before, and having an override button?
I think that's a great question. Can we use AI? Well, an obvious thing is I only looked at parsing errors, what a well-formed number is. I didn't look at the value of the number, but you could easily say with, say, location-aware systems, nobody in this location in the hospital, on the paediatric ward, say, in this bed, has had a dose of 100 milligrams of morphine, which might be perfectly sensible in oncology, but isn't sensible in paediatrics. And you could soon learn that locations or patients or whatever it is have certain numbers in certain ranges. One of the problems, well, here's an example. So you're a mother with cancer. So you might be on a high dose of morphine, because cancer patients tend to get high doses of morphine. You end up having a baby, and you get wheeled into wherever you have babies with your infusion pump, which is pumping morphine into you. So that infusion pump, which is set up to check that your dosage is sensible for an oncology patient, ends up in the paediatric ward, where it won't detect a very high dose given to a baby this sort of size, and that would be a problem. Whereas an AI system could probably say, if you get close to an environment where all the doses are low, perhaps you should be giving a low dose as well.
So is there any data where the positives and negatives are good usage and disastrous usage? Is there anything like that where we could actually start using machine learning systems?
One of the things that astonishes me is how little data there is. Yeah. And some of these devices, they keep logs. They don't keep keystroke logs. They keep the logs of the number they give to the patient. That was the problem earlier. The log said the device delivered 55 milligrams, so the nurse made an error. But if it had said the nurse typed 5 ... delete 5, well, the device has made an error, but it's all concealed in the way they work. And when the batteries go flat, they throw away the data as well. So, it's just a mess. The industry is not interested in the errors.
So, loads of questions at the back, sir. Yeah?
It seems that this is a rather naive question, because it's not my area of specialism, but a lot of the questions...
Sorry, do you mind speaking up a bit?
A lot of the issues that you're raising are already addressed in the field of information design.
Yeah.
And it seems to me there's an argument, or are you aware of any crossover from that field into, say, HCI or interface design?
That's a good point. So information design, HCI, we have known the answers to these problems for 30 years. Right? What we're doing is we're training programmers to go off and work for companies to program stuff that ignores what we know. We're failing to teach people, or possibly, a bit more charitably, is we are teaching people wonderfully, and the manufacturer is employing people who can't program at all. Maybe that's a nicer view, and we ought to be concentrating on getting certification for programmers. The solutions to most of these problems are straightforward and elementary. No, I showed a finite state machine. That's trivial stuff. People can do it if they want to. There's no will to do it, and there's no skill out there to implement them.
So we have a question also near the back, sir. Yes, please.
In their book, Understanding Computers and Cognition, Winograd and Flores took a sort of pessimistic view on this interface between humans and computers. They kind of suggested that when programmers design these interfaces, they have a very fixed view of how people are going to use an item of equipment. But when that piece of equipment is released into the real world, the contexts are so varied and massive that there's always going to be situations where things go wrong. Do you share their pessimism?
If programmers all did a HCI course and a few other courses, they would be more aware of that problem that Winograd and Flores are pessimistic about. Well, one of the infusion pump companies I went to, I met the programmers of one of the pumps, which I decided not to show here because it would be libelous if I started talking about it, but now you don't know which one it is. I met the programmer of it, and I asked him, he got a laptop and a USB cable in the back of the thing, and he was programming it. Well, how are you programming it? I asked, and he said he was using C++. Oh, how big's your program? So this is for a thing that I've built simulations of these things, and my simulations are 100 to 200 lines long, and of course I haven't got motor control and a few other bits and pieces, but that would be standard across the device range. He said his C++ program was 250,000 lines long. I said, surely that must be because it's implementing, say, a virtual machine for the range of devices. So, I can imagine the operating system and the real-time this, that, and the other is that much, but the device itself is small, isn't it? And he said, what's a virtual machine? Right. So the people programming these don't know first-year computer science. And Winograd and Flores are right to be really pessimist about it. And I think that's partly our problem for not training people with the skills to program reliably. So it's a good question, Mark. Yeah.
In the United States, there are institutional barriers to investigating errors of these kinds too closely because it's all based on litigation, and you have to find somebody to blame, and these are individuals in the hospital. The hospital will pay their malpractice insurance will pay it, but they're motivated to tighten up and keep everything secret and stonewall the investigation as much as they can. What are the institutional barriers in the UK? Are they identical, or what stops? Why is there a stop rule of the kind you're mentioning?
The stop rules are how people behave, right? It's not a rule that is imposed by the organisations. People doing a root cause analysis look at all the possible causes and they go back, and at some point you've gone back far enough and, operator error, that's the simplest explanation. You stop there. It's an observation, it's not a regulation. Okay, that's one. Let me tell you about the American situation. The FDA approves gadgets like the ones I've got there. And the law in America is if the FDA has approved it and it has not malfunctioned, then it is not at fault. Right? Next, for commercial confidentiality reasons, the manufacturers don't disclose the source code to the regulators. Right? So how do you check that a device like that is safe without looking at the source code and so on? And then the third thing, which is true but sounds even more cynical, if you want to make a device like that, what you do is you build a prototype with trivial program in it, you send it to the regulators to get it approved. Because, for instance, if I drop that in a bucket of fluid, it will keep on working. That's part of the regulatory approval. And they'll also check the buttons, light it up properly, and so on. Now I've got regulatory approval, I put in the real program, and I tell the FDA, I've updated the software, is that okay? And they basically say, sure. So you've now got a totally different user interface, which has not been checked by anybody outside of the manufacturers. In Britain, we have the NPSA, the National Patient Safety Agency. They're working with the Royal College of Art and designers to improve the ergonomic and industrial design of infusion pumps. And I mentioned I've got a EPSRC grant, didn't say it was EPSRC, but it is an EPSRC grant to carry on the sorts of studies with mannequins and so on. And the NPSA is a partner on that grant. So they seem to be excited about what we're doing, but as yet they are really followers of the FDA rather than leaders of the FDA. So Britain currently tries to catch up with what the Americans are doing, and then we get caught up with CE regulations for European stuff. So it's a very slow process. But hopefully with the 6 years of project we've got, we'll get some hard data on some of these things, and I'll then be able to answer your question. Actually, if you make the devices better engineered, you end up with safer hospitals.
Okay, can I just take one last question?
A quick observation. You've given yet another strong piece of evidence supporting a principle that I think should be followed by all governments, namely anything bought out of public funds involving software should have a requirement that the software be open source, so that it can be publicly checked, and also so that knowledge that's acquired through public funds can be publicly available for others.
Software is the most complicated thing we're producing at the moment, and we have no idea how to write it reliably on the scale that's needed. I agree with Aaron, it has to be open source. The reason it's not open source is because some companies like making a lot of money out of it rather than doing a good job.
Okay, I'm sorry if you didn't get a chance to ask a question. I know lots of people wanted to interact with Harold, which is a clear indication of how fascinating this talk has been. So thanks very much, Harold.
Okay, thank you.